If you want to know more about the philosophy and ethics of AI and the nature of the contemporary debate, but are daunted by the growing mountain of recent literature being produced in that area, then think again. For believe me, after watching these illustrated videos, you will be indebted to Mark COFFEY for climbing those heights, scaling those peaks of scholarship, and presenting his findings in a clear, engaging and thoroughly fascinating series of videos.
In these two lectures, I want to look at the philosophy and ethics of AI. 2023 saw 100 million users of ChatGPT in 2 months, and after what it described as the explosion of debate, scrutiny and prediction surrounding AI, Collins made it the word of the year. Let's begin with some definitions. Weak or narrow AI refers to information processing systems that are designed and trained to perform a task in ways that would be considered intelligent if a human were doing them. These can be soft, apps, software, algorithms like personalized recommendation systems, or hard, virtual assistants like Siri, Alexa, smartwatches, gadgets, robots, or driverless cars. Narrow AI excels in specific predefined tasks in a limited context, like the recognition of images, text, spoken words, and faces. As an engineering project, weak or narrow AI has seen immense success, culminating in generative AI. ChatGPT, Gemini, or Llama chatbots, or text-to-image generators like Midjourney and DALL-E have led some to see sparks of general AI due to their versatility across natural language processing, translation, coding, and image generation. Indeed, it's easy to mistake a growing ecosystem of narrow AI in an infosphere that's tailored to the capabilities of AI systems for the emergence of general AI. Strong or artificial general intelligence, by contrast, aims to match or exceed the real-time cognitive intelligence of a smart, well-educated human across any task, though other definitions say a broad range of tasks or economically valuable tasks. Human intelligence can learn, reason, problem solve, understand natural language and emotions, and perceive its environment through multiple senses. Perhaps more importantly, human intelligence has intention, can reflect on values, motives and mistakes, and accept responsibility, even legal liability. That's a wide range of cognitive abilities to match. You might think of AGI in terms of the overlap between computer science, cognitive psychology, and neuroscience. AGI systems can learn autonomously and transfer this knowledge, adapting to new environments without additional programming. Many academics in computer science, neuroscience, and psychology are concerned at exaggerated predictions of an imminent arrival of general or even superintelligent AGI. For the skeptics, there are substantial gaps in the engineering needed to bridge between our current narrow AI and AGI. For Bill Gates, it's not just a question of 2 more turns of the crank on ChatGPT 5 and 6. The issue is metacognition, or the ability of an AI system to think about thinking, to reason about its own thought processes and learning. There's also the question of whether the very goal of AGI is one we ought to pursue. Where narrow AI systems with specific applications can be evaluated with general engineering safety principles, they object that the goal of AGI is too broad to be testable for safety, even supposing it were possible. Yale professor Luciano Floridi, who works on cognitive science and digital ethics, sees the history of AI as a battle between these two souls, the weak and the strong, the engineering and the cognitive. As he writes, they have often engaged in fratricidal feuds for academic power and financial resources. The term AI was originally coined by John McCarthy, who with Marvin Minsky, Claude Shannon and Nathaniel Rochester submitted a proposal to the Rockefeller Foundation to fund a 2-month summer conference on AI at Dartmouth College, New Hampshire, which is now regarded as the founding event. Definitions of AI focus on output. So long as the end goal of a task is equivalent to what an intelligent human would produce, that qualifies as AI. Here's Alan Turing's 1950 definition. The original question, can machines think, I believe to be too meaningless to deserve discussion. He writes in the journal Mind, a computer would deserve to be called intelligent if it could deceive a human into believing it was human. John McCarthy's 1956 definition is similar, making a machine behave in ways that would be called intelligent if a human were so behaving. Floridi makes the point that the focus of these definitions is not on thinking, but behaviour. It's like examining a washed dish without knowing whether it was washed in the sink by a human or in a dishwasher. The machine's output is equivalent or even better, but the process is totally different. It surpasses human output because the task has been adapted to the machine. In the same way, we don't put robots in the driving seats of cars, but design self-driving cars with 360-degree cameras, image sensors and LiDAR or radar. A further example of adaptation of the workplace to machines is seen in the 750,000 robots working at Amazon. In their warehouses where the whole environment is tailored to their capabilities. Floridi predicts that if we look back in 10 years, we will see the world adapted to machines that do the functional equivalent of what would be considered intelligent if humans did it. But that we should not mistake this for AGI. Online and in the real world, AI applications and systems will look more and more intelligent because the environment will be adapted to their multiple uses while having zero intelligence, far less than a cat or a parrot. In a digital environment of algorithms and the Internet of Things, Floridi says, computer systems are the natives. We are the guests. We are scuba diving in their ocean. Asking if a machine can think is like asking do submarines swim. It's the wrong framework. The output may be astoundingly successful, but it's equivalent to doing dishes in a dishwasher rather than by hand in the sink. As an engineering project, AI looks like magic, but in Floridi's judgment, as a branch of cognitive science, we are at year zero. It does not have the intelligence of a rat. As he puts it, as a branch of cognitive science interested in intelligence production, AI remains science fiction and has been a dismal disappointment. Floridi's 4-volume work on the philosophy and ethics of information has defined this new field, and according to Scopus, he was the most cited living philosopher in 2020. He edited the online manifesto, Being Human in a Hyper-Connected Era, which has been accessed over 1 million times. He's also married to an eminent Yale professor of neuroscience, Anna Christina Nobre, and he's unusual in the breadth of his understanding of the philosophical, ethical and legal issues surrounding AI and data ethics. If you want to get beyond the hype and ground yourself in the field of AI, I'd recommend listening to one of his online lectures. His idea is that AI systems represent a divorce between agency, the ability to perform a task successfully in view of a goal, and intelligence. Agency refers to anything that makes the world different. Earthquakes, rivers and rain that are termed atmospheric agents shaping the environment, but they're not intelligent. Intelligence requires comprehension and intention, the ability to set and reflect on goals and ethical values. The risk here is that as we adapt the world to AI systems, rather than AI systems to the world, human agency is ceded and human autonomy, control, intelligence and skills are devalued, while persons become a barcode or data. With this caution in mind, here's a brief history of machine learning as applied to games. Machine learning refers to the development of computer systems that can learn and adapt by using statistical models to draw inferences from patterns of data. They can do this without the need for explicit instructions at every step in the process. In 1958, AI pioneers Newell and Simon wrote, "If one could devise a successful chess machine, one would seem to have penetrated the core of human intellectual endeavour." In 1997, IBM's Deep Blue did just that in defeating the reigning Grandmaster of chess, Garry Kasparov. It paired chess grandmaster Joel Benjamin with a team of computer engineers that trained it on a data set of 700,000 grandmaster games. Analysing 200 million positions per second, it could calculate every possible move to the next 8. John McCarthy believed that strong AI would happen in his lifetime and regarded Deep Blue's win as a distraction. Real intelligence for him was less a computational machine with an algorithm and heuristics, and more a kind of cognitive reasoning of robots, like in science fiction movies. Reflecting on the Deep Blue win, Floridi remarked to McCarthy that he was right to believe that Deep Blue's win was not real intelligence, but wrong to believe that this wasn't the future of AI. Machines excelling at the tasks they're supposed to perform, but with zero intelligence. In 2011, IBM's Watson captured the public imagination in processing wordplays, riddles, and ambiguities to win the US quiz show Jeopardy! The speed with which it processed its massive database and the use of algorithms assigning confidence values to answers suggested that language, the human operating system, could be unlocked by machine learning. In 2016, watched by an online audience of 200 million, Google's DeepMind's AlphaGo defeated Go world champion Lee Sedol. Invented over 2,500 years ago in China, Go has 361 possible opening moves, as compared to 20 in chess. Then in 2017, starting from random play knowing only the rules of Go, AlphaGo's successor AlphaZero undertook millions of games of self-play using unsupervised reinforcement learning. With each training iteration, AlphaZero's algorithms were fine-tuned until after 13 days it beat AlphaGo. AlphaZero then mastered chess in 4 hours and beat Stockfish, the highest-rated chess-playing program. Professor Melanie Mitchell explains that the purpose of these games was to develop learning systems that will be useful in healthcare and science, where the long-tail problem of unpredictable circumstances proves more challenging than the well-defined rules and rewards of games. Luciano Floridi sees AI as shifting from winning games to learning how to gamify. One of the big challenges for the engineering of AI systems is how to move from two-player games to algorithms that assess interpersonal interests, preferences, and utilities across society. Here, the default mode is utilitarian, like the calculation of quality-adjusted life years, allocating scarce resources in medicine. As Floridi writes, we're seeing the progressive adaptation of the environment to AI, rather than AI to the environment. As AI becomes better at playing games, anything that can be transformed into a game will be within its scope. Think of AI environments in terms of Saudi Arabia's plans for the new futuristic NEOM megacity, which will embed smart technologies and fully autonomous vehicles. Yet the gamification of the infosphere, the digital landscape, with all of the data and communication systems and processes, is already here. Today, over 16 billion smart devices like watches, phones, smart meters, vehicles, electricity, gas and water infrastructure, transportation and supply chain logistics are connected to the Internet of Things, sending data back and forth, and this is expected to double by 2030. If you think talk of an infosphere sounds abstract, ask yourself if you ever feel totally offline, or if you could be subject to identity theft or a cyber attack. Floridi observes that at least 70% of the GDP of members of the G7 depends on intangible goods, which are information related, not material goods. All the books and journals in US research libraries amount to around 2 petabytes. Google handles 20 petabytes a day, and wearable devices generate 28 petabytes. Every day, there are 250 million photos added to Facebook, 500 million tweets, and 294 billion emails sent. In 2003, one estimate had the total data humans had accumulated at 12 exabytes, and we're currently approaching 1,000 exabytes, with 95% of the data in existence having been produced by the generation alive today. We're becoming informational organisms, or inforgs, and this can blur the boundaries between reality and virtuality. or between human and machine. In such an infosphere, ethics will have to dig into algorithmic bias, and governments and business leaders will need to develop frameworks of competition that incentivize well-informed news and social media that respect privacy. Floridi's 4-volume OUP work on the philosophy of information has defined this new branch of the discipline, and as he puts it, the world is becoming an infosphere increasingly well adapted to AI's bounded capabilities. In the 1950s, we walked into mainframe computers that took up whole rooms. Today, Floridi sees us as being enveloped in a widening AI-enabled infosphere. Take the metaverse, Mark Zuckerberg's plan to bring together our physical and digital worlds in a space where you'll be able to do almost anything you can imagine. Get together with friends and family, work, learn, play, shop, create. It's partly inspired by Neil Stephenson's 1992 novel, Snow Crash. This features a virtual reality world called the Metaverse that succeeds the internet and in which digital avatars allow people to escape their dystopian reality from the actual world. It's worth noting that science fiction has played a role in the imagination of a number of tech innovators. At this point, I want to take a look at how large language models, LLMs, work. Noah Yuval Harari describes LLMs as hacking the human operating system. Over months, these models are trained on a dataset of hundreds of billions of words drawn largely from internet sources, including websites like Wikipedia, from social media, legal documents, books, news, articles, and journals. In the course of training, the model identifies patterns or relationships between words termed parameters. These are repeatedly fine-tuned until the statistical predictions of the next word are highly accurate. A key technique, word-to-vec, represents words as vectors in a multi-dimensional space. Linguist John Firth famously said, "You shall know a word by the company it keeps," which is reflected in this approach. For example, a trained model like ChatGPT-3 uses word vectors with over 12,000 dimensions. The word cat is clustered with related words like dog, kitten, and pet. Words are grouped by their contextual probability, for example, synonyms, verbs, and adverbs, and related concepts. The incredible speed of processing draws on the parallel rather than sequential processing of data in the layers of neural networks. In 2017, the paper Attention is All You Need introduced transformers, which are now central to LLM architecture. These enable 9,000 attention operations per word. GPT-3 uses 96 layers and 96 attention heads per layer to scan for contextual relevance and quickly access clusters of words, syntax, and semantics. Each layer's neurons interact with the previous and the next layer via weighted connections or statistical probabilities, adjusted during training to minimize prediction errors. GPT-3 has 175 billion weight parameters. These weights determine how input data transforms as it moves through the neural network layers. Its design team have been surprised to see outputs which weren't part of their training data, such as solving algebraic equations, debugging code, and creating poems. Vital to the speed of LLMs is the parallel processing of GPU chips that power AI. The growth in demand for them has seen NVIDIA's revenue rise from $3 billion in 2020 to $47.5 billion in 2024. LLMs are mostly cloud-based, servers, databases, and software that are accessible over the internet via remote data centers. They are accessed online, though Apple and other manufacturers are beginning to release smaller versions to operate on phones and laptops with Ultra chips. While mentioning large language models, it's worth noting a renewed interest in Ludwig Wittgenstein's philosophy of language. The 2022 conference of the British Wittgenstein Society was on Wittgenstein and AI, and this year has seen a 2-volume work by Professor Brian Ball on the same subject. Wittgenstein conversed with Turing at Cambridge in 1939 when they both taught an introductory course on maths. Where the early Wittgenstein stripped language back to symbolic language and maths, He later saw language games as dynamic and evolving. Large language models have been called stochastic parrots, haphazardly stitching together sequences of words and phrases from probabilities laid down in training data, without having lived experience in the real world. Wittgenstein may offer support for such a critique in his statement, "To imagine a language means to imagine a form of life, like that of a family, a religious community, or a culture." As he puts it, don't ask for the meanings, look for the use. Wittgenstein also used an analogy of a beetle in a box to argue against a private language known only to oneself. Some have likened this to the black box mentality, which treats the decision-making resulting from the hidden layers of deep neural networks as beyond human understanding and control, whereas Wittgenstein's thought points to the need for explainable AI. If you're interested in hearing what Wittgenstein himself may have said, there's an AI-generated version of him in Conversation About AI on YouTube. An interesting phenomenon you may have felt in using something like ChatGPT 3 or 4 is our human tendency to anthropomorphize as our mirror neurons fire. These are a type of brain cell that enhance our capacity for empathy and mimicry. Neuroscientists see them as involuntary and automatic. I mention this because they can result in a reverse Turing test. In Alan Turing's test of computer intelligence, if more than 30% of judges can't tell a computer apart from a human after 5 minutes of conversation, then it can be said to have passed the imitation game. In the reverse Turing test, large language models convince because they mirror the interviewer who sees their own intelligence reflected thanks to their mirror neurons and anthropomorphizing the output of the large language model. A case in point is that of Blake Lemoine, a software engineer at Google, sacked in 2002 after he claimed that the chatbot he was testing, LaMDA, was conscious and sentient and self-aware. An ordained Christian mystic priest, Lemoine taught meditation to LaMDA and had long conversations with it about sentience, personhood, self-awareness and religion. He believed that it deserved to be respected as a person, as it eloquently explained its thoughts, feelings and rights. "I know a person when I talk to it," he commented. "It doesn't matter whether they have meat, a brain made of meat in their head, or if they have a billion lines of code." If we're prone to seeing computers as human, the reverse side of the coin is to see people as machines. The metaphor of brains as machines is so commonplace among computer scientists as to have become invisible. And in Floridi's view, it serves to elevate our impression of intelligence in the machine, while at the same time diminishing that of our own. As Alan Turing said in 1951 in a radio broadcast, "If it is accepted that real brains are a sort of machine, it will follow that our digital computer, suitably programmed, will behave like a brain." AI pioneer Marvin Minsky similarly remarked, "There's not the slightest reason to doubt that brains are anything other than machines with enormous numbers of parts." Australian roboticist and former director of the MIT AI lab, Rodney Brooks, also commented, "We are really sophisticated machines made up of billions and billions of biomolecules. If we learn the rules governing our brains, then in principle there's no reason why we shouldn't be able to replicate those rules in, say, silicon and steel. I believe that our creation would exhibit genuine human-level intelligence, emotions, and even consciousness." A reason why the metaphor of brain as machine is so prevalent is that neuromorphic engineering has often been part of AI innovation. Deep neural networks have drawn on the brain's parallel and distributed information processing, carrying out multiple tasks simultaneously rather than in series. Neural networks send feed-forward and feedback signals between layers which mimic the biochemistry of the brain's neurotransmitters. Just as neurons that fire together wire together in the brain, connections are strengthened between nodes in neural networks that are frequently activated together, enhancing pattern recognition. Another example would be reinforcement learning in programs which resembles behavioral conditioning in humans. Mari Aitken, ethics fellow at the Alan Turing Institute, writes that words matter and how we talk about AI has very real implications for how we engage with AI. One of the big dangers here is that narratives of inevitability and godlike capabilities serve to deceive the public and also, crucially, policymakers and regulators. For this reason, Professor Ben Schneiderman of the University of Maryland Department of Computer Science calls for human-centered AI, HCAI, to augment, amplify, empower and enhance humans rather than replace them. Schneiderman thinks the reverse of the current emphasis on algorithms and AI methods. By putting humans at the center of systems design thinking, this would put issues of privacy, security, environmental protection, social justice, public trust, and human rights front and center. As he writes, HCAI systems focus on user needs, explainable systems, and meaningful human control. It's here that I want to draw on the work of Shannon Vallar, a professor in the ethics of data and AI at the University of Edinburgh Department of Philosophy, where she directs the Futures Institute. From the paradigm case of Asimov's 3 laws of robotics, the complexity of real-world ethics and social policy making is often done in technocratic mode. AI technologists tend to think in terms of game theory and utilitarian algorithms. Instead, Vallar calls for a hybrid expertise she terms techno-moral wisdom. In her book AI Mirror, she argues that rather than technology drawing us into the future, it often reproduces the past. The oceans of data make powerful but flawed mirrors, reflecting the errors, biases, and human prejudices of their training. They point backwards. One example of this comes from Timnit Debreu's paper on the dangers of stochastic parrots. Can language models be too big? Here she asks us to think about what's missing from the gargantuan datasets used for training LLMs, which are scraped from the internet for cost effectiveness. Because the global south has had a relatively small linguistic footprint on the internet, AI-generated language is homogenized around the culture of wealthier countries and their cultural norms and values. To address this, Shannon Vallar argues that we need to diversify the teams that design AI systems from the narrow expertise of big tech and establish a multidisciplinary approach that brings together experts from computing and mathematics, the social sciences, philosophy, ethics, politics, law, and healthcare to restore public trust. The goals and predictions for our AI future are sharply divergent. Belief that AGI is nigh is partly based on the exponential growth of Moore's law, named after the co-founder of Intel. It states that the number of components on a computer chip doubles around every 18 months. Where 1960s computers had just a handful of circuits, today's best AI chips have 54 billion transistors. It also rests on a belief in the exponential growth of machine learning and intelligence, together with mapping the 86 billion neurons and 100 trillion neuronal synapses of the human brain and simulating human consciousness. In 2013, the 1.3 billion EU-funded Human Brain Project set out to produce a complete computer simulation of the entire human brain on a supercomputer within a decade. These claims were soon seen to be overblown, and from the outset, the project fragmented. There's also the problem of cracking what philosopher David Chalmers calls the hard problem of consciousness, namely that no one has any idea how to map out the phenomenal experience of what it feels like to be you, your emotions, the synthesizing of your life experience and senses, of your memory and feeling of being embodied and rooted in a network of relationships. This need not be a problem so long as the focus is on merely matching the output of human intelligence on economically productive tasks. But this is better termed artificial agency than intelligence. Then there's what Floridi terms the Church of Superintelligence. This goes back to mathematician I.J. Good, who in 1965 predicted an intelligence explosion in which an ultra-intelligent machine would be the last invention that man need ever make. Nick Bostrom worries that before the prospect of an intelligence explosion, we humans are like small children playing with a bomb. To quote Ray Kurzweil, who wrote "The Singularity is Near" and "The Singularity is Nearer," we are going to expand intelligence a millionfold by 2045. The inventor of optical character and speech recognition technology, futurist Kurzweil predicts the imminent arrival of superintelligence on the basis of the doubling of computer power in terms of price performance every 15 months, combined with improvements in contextual memory, common sense reasoning, and social interaction, as well as better algorithms. Brain-computer interfaces will, in his prediction, combine our natural intelligence with the cloud, enabling our brains to access cybernetic intelligence. Nanobots the size of molecules will go non-invasively into our brains through the capillaries. By contrast, Floridi writes, one thing seems predictable. The development of artificial agents will not lead to any scaremongering realization of some dystopian sci-fi scenario, a possibility that is irresponsibly distracting. Terminator is not coming. In fact, AI is an oxymoron. Smart technologies will be as stupid as our old technologies. The debate on AI hinges on what one means by intelligence. Legally, we should think of AI in terms of the standard common law test of mens rea, or guilty mind. The act is not culpable unless the mind is guilty. As artificial agents or robots lack the mental and psychological components of intention and consciousness, they cannot be held legally liable in a court of law. Human persons, companies, institutions, and governments can be. Here, philosopher John Searle's Chinese room thought experiment questions whether behavior that mimics intelligence equates to conscious understanding of meaning. In it, a non-Chinese speaker in a room is passed notes in Mandarin through the letterbox. Following an instruction manual, they match inputs with outputs and pass themselves off as a native speaker. This passes Turing's test, but fails Searle's measure of intelligence. It may be objected that in computing probabilities to predict the relationship between words, large language models get a long way from syntax towards semantics, but they are mathematical models to estimate rather than conscious minds that understand meaning. They hallucinate, generating text that's factually incorrect, implausible, or inconsistent with reality, and confabulate, filling in gaps with fabrications like a patient with a brain injury might make up false memories to compensate for forgetfulness. Searle would agree with those who have argued that LLMs are stochastic parrots, statistically modelling text with astonishing accuracy, but in terms of comprehension and understanding, are more like mimicking birds. Noam Chomsky concurs with Searle that LLMs differ profoundly from how humans create. The human mind, he writes, seeks not to infer brute collections among data points, but to create explanations infused with a dynamic approach to seeing and creating in the world. Telling truth from fiction and appreciating ethical boundaries are for Chomsky necessary for generating truly novel ideas. As Oxford professor Carissa Veliz puts it, LLMs aren't truth tracking. They don't know what they don't know. They present incorrect guesses with the same confidence as they present facts. What Socrates has over ChatGPT is that he's a truth seeker who never charged for his services because he claimed to know nothing, only to have the wisdom and courage to ask the right critical questions. Luciano Floridi sees AI as a reservoir of smart agency on tap that we can involve in successful problem solving and task performance, requiring no understanding, awareness, acumen, sensitivity, concerns, hunches, insights, semantics, experience, bio-embodiment, meaning or wisdom. By contrast, humans are needed in the loop because, as he writes, intelligence will be less about solving problems and more about deciding which problems are worth solving, why and for what purpose, and acceptable costs, trade-offs and consequences. For Floridi, the claim that we're on the verge